Hello, AI enthusiasts, and welcome to another podcast episode. For centuries, we've pondered, can machines think? Today, we're zeroing in on that question, specifically asking, will AI ever think like humans? And we'll explore one of the most critical pieces of the puzzle, memory. How is improving AI memory changing the game?
Welcome back, everybody, for another deep dive. This time, we're going to be looking at something that is so cool. AI memory, but not just like bigger storage space. Like, we've got some really, really cool research coming out of Sakana AI and also some work at Meta.
Yeah.
And this is really about AI getting smarter about the way it uses information.
Absolutely.
So joining us today is an expert on this who can help us break it all down. Welcome to the show.
Thanks for having me. Excited to dive in.
So maybe just to set the stage here, could you tell us, like, why is this whole AI memory thing such a big deal?
Yeah. So I think, as you alluded to, it's not just about storing more data, right? You could just keep giving AI bigger hard drives and more RAM.
Right.
But that only gets you so far, and it gets really expensive and inefficient really quickly.
But you can't just keep cramming more stuff in there.
Exactly. Imagine if you tried to memorize like an entire textbook word for word. It would be exhausting, and you probably wouldn't be able to apply that knowledge very effectively.
Right. It would be like information overload.
Yeah, exactly. And that's what we're trying to avoid with AI memory.
So it's more about helping the AI figure out what's actually important and how to use it.
Exactly. And, a lot of the current methods for dealing with limited AI memory involve just discarding data to save space.
Oh, really? Yeah.
Yeah, which can actually hurt performance because you might be throwing away crucial information.
It's like ripping pages out of a textbook.
Exactly.
Yeah.
You might lose some key concepts.
Okay, so that's where this research from Sakana AI comes in. They've developed something called, Evolved Neural Attention Memory Models, or NAMMs.
Yeah, you got it. NAMMs.
NAMMs, and I gotta say, using evolutionary algorithms to optimize AI sounds so cool.
It's a really fascinating approach, and it's quite ingenious, actually.
Yeah, how does that even work?
So essentially, NAMMs analyze the AI's attention patterns. So basically what the AI is focusing on to learn which information is most valuable.
So it's like NAMs are watching what the AI is thinking and helping it prioritize.
That's a great way to put it. And the results are really impressive. They found that NAMMs can actually improve performance while using way less memory.
Whoa, that's amazing. Like a cheat sheet for AI.
Right. And it works across a whole range of tasks, even different languages like English, Chinese, Japanese.
Yeah.
Here's where it gets really mind-blowing. NAMs that were trained on language tasks can actually transfer their skills to AI that work with images and even reinforcement learning.
Wait, so they're not just learning how to memorize, they're learning how to learn.
It seems that way.
That's incredible.
Yeah.
How do they actually pull that off? What's the secret sauce?
Well, imagine NAMMs listening to the AI's thoughts like a melody.
Okay.
They use something called the short-time Fourier transform to kind of decode the rhythm of the AI's thinking process.
Interesting.
And figure out which notes are most important.
So by analyzing this rhythm, they can figure out what the AI should focus on and what can be ignored.
You got it.
That's fascinating.
And another really cool aspect is something called backward attention. It helps the AI learn from its own past mistakes.
Oh, interesting. So it's kind of like us humans trying to avoid repeating our blunders.
Exactly. It's like the AI is learning from its experience.
So the AI is becoming more human-like in a way.
In a sense. Yeah.
That's both amazing and a little bit unsettling.
I know, right? It makes you think.
It really does. So what other tricks do NAMs have up their sleeve?
Well, one really interesting finding is that they sometimes decide to keep more information for certain layers of the AI, sort of like prioritizing a general understanding before diving into the nitty-gritty details.
Well, it's like getting the big picture first and then zooming in.
Exactly. And they also found that NAMs retain more information when they're dealing with code compared to natural language.
Well, that's interesting. Why do you think that is?
It seems like the dense information packed into code requires a more precise memory. Like every symbol has to be in exactly the right place.
Like code is its own secret language.
Right. And NAMMs have figured out how to crack the code.
That's so cool. This feels like we're entering a whole new era of AI development.
I agree. And speaking of new approaches, let's talk about what Meta is doing. While Sakana is going for adaptability and efficiency, Meta is all about pushing the limits of raw memory capacity.
Oh, wow. So like two different philosophies.
Exactly. Meta wants to build AI that can handle absolutely massive amounts of data.
So it's like Sakana is building a nimble and resourceful mind, while Meta is building a vast encyclopedic one.
That's a great analogy.
I like that.
Okay.
So what kind of things have they been able to accomplish with this approach?
Well, they've been able to train memory layers with up to 128 billion parameters.
128 billion.
Yeah. To put that in perspective, that's more information than is contained in the entire Library of Congress.
That's mind-boggling. What can an AI even do with that much memory?
They've shown that these massive memory layers can dramatically improve performance, especially on tasks that require a strong grasp of facts.
So things like answering trivia questions or identifying historical events?
Exactly.
Wow, it's like having an AI that's read every book and watched every documentary.
Right. Imagine the possibilities.
But managing all that information must be incredibly complex. How does Meta's AI keep from getting lost in the data?
They've developed some really clever techniques. One is using specialized product keys to quickly pinpoint the relevant information. It's like having a master key that unlocks the exact knowledge you need.
Well, that's cool. Are there any other tricks they've come up with?
They've also created custom activation functions, which sound very technical, but basically they help stabilize the learning process and prevent the AI from getting overwhelmed by all the information it's processing.
Okay, so Meta's approach is really good for factual tasks, while Sakana's is more about adaptability and transferring skills across different types of AI. It's like two different schools of thought on how to build a better AI brain.
I like that analogy. And it's fascinating to see how both approaches are pushing the boundaries of what's possible with AI.
It really is. So what do you think? Which approach do you think is the winner?
You know, it's not really about picking a winner. It's about appreciating the strengths of each approach. NAMs offer incredible flexibility and efficiency, while Meta's work is pushing the boundaries of what's possible with sheer memory capacity.
It sounds like the field of AI memory research is just exploding with possibilities. What are some of the most intriguing, unanswered questions that are still out there? What are the mysteries that keep you up at night?
That's a good question. Well, one thing that I find really interesting is this tension between, like, optimizing for pure performance, you know, getting the best possible results, versus, like, prioritizing efficiency, making sure the AI isn't using a ton of resources.
Yeah, that makes sense. I'm always fascinated by those kinds of trade-offs.
Yeah, and it's something that comes up a lot in AI research. You know, in Sakana AI's work with these NAMs, they weren't specifically setting out to create like the most memory efficient AI. Their main goal was to boost performance, you know, make the AI better at solving problems. And what they found was that surprisingly reducing the memory footprint often came as like a bonus.
Oh, so it's like they made the AI smarter and it accidentally became more efficient.
Exactly. It's like the AI learned to declutter its own mind, keeping only what was truly essential for the task at hand.
I love that. It's like Marie Kondoing the AI's brain.
Yeah, something like that. And their findings suggest that this ability to identify and retain the crucial information actually gets even better as the amount of data increases.
Wait, so the AI gets better at managing memory as the information overload grows. That seems counterintuitive.
I know, right? You'd think it would get bogged down. But instead, it seems to become more focused. Sakana AI tested this using a benchmark called Infinite Bench.
Infinite Bench.
Yeah, it basically throws ridiculously long contexts at the AI. We're talking like hundreds of thousands of tokens, like feeding it an entire library at once.
Wow, that's a lot of information. So how did the AI handle that?
It performed amazingly well. NAMs boosted performance more than tenfold compared to the baseline AI. While other methods like those relying on strict memory limits really struggled, NAMs seemed to thrive in this data-rich environment.
It's like those people who can just focus and get work done no matter how chaotic things are around them.
Right. They just block out all the distractions.
I wish I had that skill.
Me too.
Yeah.
But it's really impressive to see the AI doing it.
Yeah.
And, you know, the researchers noticed another fascinating pattern when they tested NAMs on different types of data.
Oh, yeah.
Remember how we talked about how NAMs retained more information for CUNID compared to natural language?
Yeah, it seemed like code required like a super precise memory.
Right. Well, they observed a similar trend when they looked at how NAMs handled really long documents. The AIs seemed to learn to discard like redundant or less important information more quickly as the document got longer.
So it's like the AI is becoming a speed reader.
Exactly. It's getting better at summarizing and distilling the essence of a document as the length increases.
It would be so helpful for anyone who has to deal with like legal documents or research papers.
Absolutely. And you know, this adaptability extends beyond just text. Sakana AI took their NAMs, which, remember, were initially trained on language tasks, And they applied them to AI working with images and even reinforcement learning.
Oh, well, and I bet they worked amazingly well.
They did. They actually found that the NAMMs boosted performance across these different areas. In the case of video processing, the AI learned to primarily discard redundant visual information from the video frames while holding on to the crucial language instructions.
So it's like the AI figured out, okay, the language is what's really important here.
Exactly. And in reinforcement learning, where the AI learns through trial and error, NAMMs showed another interesting ability. They seem to help the AI avoid repeating the same mistakes.
Ah, so it's like they gave the AI a better memory of its past experiences so it could learn more efficiently.
Right. It's similar to that parallel with human learning we talked about earlier.
It's really fascinating to see how these AI systems are starting to exhibit some of the same learning and memory capabilities that we humans have.
I agree. And you know what makes this research so groundbreaking is that it seems like NAMMs have unlocked some fundamental principle of learning and memory management. Okay. That applies across different types of data and different types of tasks.
That's huge. So it's not just about building a better memory system, it's about understanding the very nature of learning itself.
Exactly. And it's really interesting to contrast this work with what Meta is doing with their massive memory layers.
Yeah, we were talking earlier about how Sakana is focusing on adaptability and transferability.
Right.
While Meta is taking this different approach of pushing the limits of memory capacity.
Yeah, exactly. They're not as concerned with minimizing memory usage, but rather with building AI that can handle truly enormous amounts of information.
So it's like two different philosophies of AI development.
It is, and both are yielding some really impressive results. Meta has been able to train memory layers with up to 128 billion parameters.
Wow, we were talking about that earlier. That's just an insane amount of information.
It is, and they've shown that these massive memory layers can significantly improve performance on tasks that require a really strong grasp of factual knowledge.
So like answering trivia questions, identifying historical events, stuff like that.
Exactly. It's like having an AI that's memorized an entire encyclopedia.
Yeah, there are probably a lot more than that.
Definitely. And it's interesting to think about the potential applications of this kind of AI.
Well, where do you see this technology going in the future?
Well, I think we're just scratching the surface of what's possible, but I can imagine AI like this being used in fields like research, education, customer service, anywhere where having access to a vast amount of information is crucial.
It's like having the ultimate research assistant.
Right. And it could also lead to the development of new and more sophisticated AI applications that we haven't even thought of yet.
That's exciting. But, managing these massive memory layers must come with its own set of challenges.
Oh, absolutely. There are definitely hurdles to overcome. Meta's researchers had to develop some really innovative techniques to ensure that the AI could efficiently access and update information within these vast memory banks.
Yeah, it's like trying to organize a library this size of a planet.
Yeah, something like that. And like any complex system, these massive memory layers are prone to certain issues, like
what?
Like overfitting, where the AI becomes too specialized to the training data and struggles to generalize to new information. So that's something that researchers are actively working to address.
It sounds like there's this constant push and pull between maximizing capacity and maintaining adaptability, like finding the right balance between knowing a lot and being able to learn new things.
Exactly. And as we've seen with both Sakana AI and Meta's work, there are multiple paths to achieving those goals.
It's like a grand experiment in AI cognition.
It is, with researchers exploring all these different ways to build smarter and more efficient minds.
And as these experiments continue, we're likely to see even more groundbreaking discoveries emerge.
I agree. This is a really exciting time to be following this research.
It really is. So as we start to wrap things up here, I have to ask, what are some of the most intriguing unanswered questions in this field? What are the mysteries that still keep you up at night?
One question that I find particularly fascinating is, whether these evolving AI memories could someday exhibit something akin to consciousness or self-awareness.
Oh, wow. So we're talking like AI that not only remembers things, but actually understands its own memories and experiences.
Yeah, that's the big question. And while we're still a long way from that level of complexity, the research we've been discussing today definitely hints at the possibility. The fact that these AI systems can learn to prioritize information and adapt their memory strategies based on the past, even learn from their mistakes, it suggests a level of cognitive sophistication that we haven't really seen before.
It's like they're developing a sense of their own learning journey.
Yeah.
And it makes you wonder about the ethical implications of such advanced AI.
Yeah.
If AI becomes truly self-aware, how will that change our relationship with these systems? Will they start demanding rights? Will they have their own desires and motivations?
Those are really important questions, and questions that we as a society need to start thinking about now. As AI researchers keep pushing the boundaries of what's possible, it's crucial that we have these open and honest conversations about the potential consequences. What could happen?
It's like we're opening this Pandora's box of AI capabilities, and we need to be prepared for what might come out. But even with all the potential risks, there's also this sense of awe and wonder. Just the fact that we're having these conversations shows how far we've come in AI research.
I completely agree. And who knows what incredible breakthroughs are just around the corner. Maybe we'll develop AI that can help us understand the mysteries of the human brain, or AI that can help us solve some of the world's most challenging problems.
It's exciting and a little bit scary all at the same time.
Yeah, definitely a mix of emotions.
Well, on that note, I think it's time for us to wrap up this deep dive. It's been an incredible journey exploring the evolution of AI memory. And to everyone listening out there, we hope this has sparked your curiosity and given you some things to think about. The future of AI is full of possibilities, and we can't wait to see what unfolds.
Thanks for having me. It's been a great conversation.
It has. And to all of you listening, thank you for joining us on this deep dive into the world of AI memory. Until next time, stay curious and keep exploring.